Hello, my name is Dalton Yerke. I am an electrical engineering major here at Utah State University, and I'm currently a senior in the engineering program.
My name is Nathan Kwong. I am also an electrical engineer here at Utah State University. This will be my third year here studying the subject.
Today we are proposing our final project for our ECE 3710. We've decided to do an accelerating fan which changes speed according to 3 input buttons. And this is using a stepper motor which we have modified to use full stepping and half stepping. In order to complete the accelerating fan, one requirement was to create an actual fan blade. And this is the fan blade that we designed. This was designed using the Idea Factory at Utah State University and using SolidWorks. Due to our lack of knowledge of SolidWorks, we made a simple configuration of fan blade system. As you can tell, there's a total of 12 fan blades. This was just due to personal choice. Each fan blade is approximately 3 inches in length. This creates a full 6-inch fan blade in diameter. This is used to make sure that we can actually see how fast the fan is moving given a specific interrupt. The bottom of the fan has a 0.25 inch by 0.125 inch rectangle. This is so that the fan blade can actually sit on top of the stepper motor without moving or getting stuck permanently. Each fan blade is also 1 inch in height. This is due to making more critical points here attached to the main circle, which also provides proper structure for the fan. The circle here is hollowed out so that the fan blade has less mass to it. This allows the fan blade to actually move properly on the motor without compromising the motor system. This can be done by increasing the negative torque on it or allowing too much mass for the stepper motor to actually rotate. And this is the fan blade that we are using for the project.
As you can see here, this is our configuration for our final project. Our final project is using interrupts using these particular buttons to control this particular DC motor. The interrupts are controlled by these buttons. These buttons are connected to these particular GPIO pins, GPIO A0, A1, and A2. Now, the reason why these resistors are here is because this particular configuration is set to a pull-down configuration, and the GPIO pins themselves are set into open drain. The reason why we want to set the GPIO pins into open drain configuration is so that when these buttons are pressed, it'll read high, and when they're not pressed, they'll read low. Now, the reason why these resistors are here is so that we can, when we have it configured and pulled down, it can only sink so much current. The maximum amount of current the GPIO pins can sink itself is 20 milliamps. Thus, the resistors are needed to sink the current even more. Now, moving on to the stepper motor here, as you can see, the stepper motor is connected to GPIO-C here and just connected to a 5.5 volt source here and connected to a common ground to the board. All right, as you see here, this is one of the several functions we have for our final project. Our first function that we used was a delay function. This particular function here doesn't necessarily do anything. All it really does is provide a delay such that the stepper motor doesn't burn itself out, and also for the initialization sequence. Speaking of which, moving into the initialization part, what we have here is we're just going to initialize the GPIO ports and their clocks. However, one thing we want to mention here is that we enable the MSI clock instead of the default clock. The reason for this is so that we can set the MSI clock, which has the highest clock frequency for our particular microcontroller, so that we can achieve the speeds necessary that we outlined in our design document. Here we have the configuration for the interrupts for PA0, PA1, and PA4. This is our initialization for the SysTick handler. It's just going to initialize the SysTick and take in a value. Our reload value is roughly about 100,000. These are the IRQ handlers for all these particular interrupts, what it's going to do here is if the red button is pressed, it's going to set the flags for both of the run and run 2. Run in this particular case will be for the slow motor, run 2 will be for the fast motor. It will just set them to 0 so that when it goes into SysTick or the SysTick handler, it just won't run. Same idea for the green button, except for we're going to set the run flag so that it goes into the fast motor. Moving on to the yellow button, we're going to set the run flag to 0. We're going to set run 2 to 1 so that it runs faster. Now, moving into our slow motor function and our fast motor function, they're virtually identical except for the fact in our slow motor function, we're using half stepping due to the speed requirement that we outlined in our design document. In our in our fast motor, we are using full stepping to achieve the speed we meant, as I mentioned earlier. Here's our SysTick handler. That's just going to check the flags and send them to the correct functions. Here's our main function to run the entire code.
As outlined in our project proposal, we have specific requirements to complete this project. First, we must have an input. We decided to have an input of 3 or more buttons. 1 to make the fan run at a high speed, 1 button to make a fan run at the low speed, and run to stop the fan. The project must use a DC stepping motor, which you can see is here. And the project must use the SysTick handler, which was shown in the code previously. The project also needs a physical fan, which we use right here, which was made through 3D printing. Now I will test the project. I will press this green button and the fan will start running at a high speed. I can stop it here pressing the red button. I can press this yellow button to make the fan run at a low speed. I can stop it here. And due to that delay function, we have to wait a little bit before the fan will stop. There it is. We can also change the speeds while the fan is running. So for example, I can run this fan at a high speed, and I can click the yellow button and it'll run the fan at a slow speed. It does not have a delay because when the fan is running in the fast state, there is no delay function involved. And I can also halt the fan again. And again, we're waiting for the delay function to kick in. There it is. We can go the other way around too. So we can start the fan at a low speed. And then I can hit the green button and it should speed up after a delay. And then we can also stop the fan. And this concludes the testing of our project.
We learned a lot about the design process as engineers need to go through, from the idea phase to the actual physical design of this project. We started our idea with just thinking, maybe we can just use some interrupts and design a fan. Little did we know that the actual process itself took a little longer and there were a couple more steps. For instance, we had the idea, we needed to create a proposal for this idea, which we wrote prior to this, had to get that approved. Then we actually started designing the project. Now in the design phase of the project, as Dalton mentioned earlier, we had to learn how to use SolidWorks to create our fan. And along with that, we need to also reconfigure a lot of our code that we've learned previously to actually do what we wanted to do. For instance, we had to reconfigure our SysTick handler and our interrupts such that it would take in those particular GPIO ports and those particular speeds and modify it so that the functions for the slow and fast motor, as shown before, would work. And at the end, we learned a lot about actually implementing our design. And as you can see, we were able to implement our design to the fullest part of what we wanted.
This concludes our final project for ECE 3710 at Utah State University. Thank you.